Hello everyone, Atheatos here, and this time with a UMC 486 motherboard, the MB457 version 1.1. Now there are many motherboards like this, with a different model and from different brands, and all share exactly the same layout. The main thing here is that, this is a compact 486 motherboard that doesn't have CAS and only has ISA slots based on the UMC UM8498F chipset. Now there are two options for the CPU. This can come either with a QFP CPU or a PGA socket. Yeah, for sure this is a socket 1 motherboard. Now the interesting thing and the reason I'm making a video about this now is that when you have a QFP CPU, it is usually this one, the UMC U5SX. This is a well-known 486 clone that basically overperforms the Intel ones. So according to Wikipedia, this is known as UMC Green CPU. And mainly these are 486SX CPUs from 25 to 40 MHz. And there are a few variations, but more or less all these have the same core. The only different one is the U5D, that is really a 486DX CPU. But this is so rare that it is actually unobtainable. The most common part numbers is the U5S and the U5SX. And of course all these motherboards have the U5SX, as these are the ones that are released in the PQFP package. Now the critical thing is performance. This is a heavily optimized core, and some functions are highly accelerated. As an example here, integer division normally takes 40 cycles, in this CPU it's only 7. So in the end, here Wikipedia says that the 40 MHz U5S actually performs very similarly to a 486SX2 at 66 MHz. Yeah, this is quite amazing, but we will see today. Now the other interesting thing is of course that Intel sued them for patent infringement, and in the end they were forced to remove all their CPUs from the market. That's why many of the CPUs have the marking not for US sale or import. So UMC also had plans for a U486DX2, but due to all these lawsuits and stuff, in the end they stopped production. Apparently there were a few engineering samples. I cannot even imagine what would have happened if these were ever released. So now what else is here to say about this motherboard? Up here are the jumpers where you can select if you want to have the QFP or the PGA CPU. Up here is the clock generator and the clock buffer, and 3 jumpers to select the bus speed. Then 2 jumpers down here to select between SX or DX. And that's all with the jumpers more or less. This is the BIOS chip. And there is no keyboard controller or real-time clock chip. Both of these are integrated in the main chipset. So overall a very minimalistic board. Now my motherboard here, I got it as Brocken. So it was listed as 4 parts. And if you see here, there is only minimal battery damage and no cut traces. Then I checked all the pins around the chips, both the CPU and the chipset, and all were firmly attached. Then for sure I plugged it and it was dead. No postcodes, no activity, nothing. Now I checked the basics, power supplies, clocks and stuff, and are okay. The reset signal is also okay. So let me demonstrate actually. And here we go. Nothing. In a case like that, you want always to check the reset. So when you hit the reset, you should get a reset here, and when you leave the reset after a while, you get it back. So basically that means there's no easy fix for this motherboard, and this is the reason I'm making this video today. I did more checks, and more or less I suspect that the problem is with the main chipset, and I have already bought a few replacements. But first I will walk you through to what I checked, and I'm more or less 100% sure this is the chipset. So when I have a motherboard that doesn't work, the first thing I check always is the reset, because if the motherboard is stuck on reset state, this is a different story. It might be a jumper, or it might be here the PowerTech is cut somewhere, or maybe the reset logic is problematic. Either way, if you're stuck in reset is a different case than this one. Then the next point that you should always check is the BIOS. You can try another chip with a fresh BIOS and see if there is any difference. So then if this doesn't work, you should just remove the BIOS chip. These BIOS chips usually are always the same. It's the 27C512. And what we want to check is the connectivity here on the socket. And the fastest way to do that is to put your multimeter in diode mode, place the red on the ground, and then go one by one and check everything. Up there I have the pin out of the BIOS chip, And what we want to see here is a diode, basically something like 0.6. If we see something that it is unconnected, it is a problem, and we need to see where the line is cut. And if we see something to 0 is also a problem, that means that probably something is burned on the motherboard. So here we go, so far so good. Here this is unconnected, and here this is sorted. Yeah, looks like all the data lines read as unconnected, but this is probably not true. But the worrying thing is this here, this is data 1, and it is definitely sorted. Let's go in ohms, and we check between ground and this. So this is not connected, but this data 1 is 10 ohms to the ground. So this looks like problem here. The other data pins are the same, it's kilo ohm. By the way, this BIOS chips basically connects here to the ISA bus, and here we have again the data and then the address. So if any of these pins is shorted or unconnected, it's also a problem. Let's check a bit. But then this is again data 1, it is sorted. So this is the problem that stops this motherboard from booting, posting, whatever. And at this point, I should also mention some basics. So this is the main chipset here, and this connects with a bus to the CPU. And then the same data bus is shared with a memory, but the memory has another address bus that connects again to the chipset. Then finally, the ISA is a totally different bus that connects directly to the chipset. So any problem with the ISA bus, any short here, probably points directly to the chipset. There might be a few cases where you have some buffers between, but yeah, on this motherboard there's no buffers. There are some buffers here, but these are different for other signals. This chip here, I don't know exactly what it has because the datasets are not there. It is probably the DMA controllers, maybe the keyboard controller, in general something like a peripheral controller. So let's see, just as a confirmation, but this for sure. We have here data 1, and I have traced it already, it is somewhere around here. Where are you? This 10 ohm doesn't count. Yeah, here we are, 1 ohm. So yeah, definitely the data signals come from the chipset. Now at this point, this is already good enough indication that the chipset is burnt. But okay, because I have the equipment, I did some voltage injection. I put here my power supply at 1 volt, and I injected this directly into data 1. This is only 100 milliamps, so the total there is 0.1 watt. Yeah, this is very low and probably very hard to detect. But in the end, okay, if you leave it a little bit like that, the only thing that gets a bit hotter is the chipset. Yeah, here everything is around 31 degrees. This is the ambient temperature, and the chipset is at 34. And this is a closer up view. So again, everything points to the chipset. Now, replacing this is way harder than replacing a 386 CPU. So yeah, I'm gonna do it off camera. Then for the chips here, unfortunately some of the pins are bent, and this is crucial to be straightened up before I try. So yeah, that's all for now. Wish me the best. So first step here, yeah, very classic. I just flooded the chip with flux and low melt solder. And then okay, I removed the chip with a hot air gun, wicked it, cleaned it, and yeah, here we are. Now of course this is the easy part. Then okay, we go for some footage from the microscope. And again, this is not the best, but okay. So here again, very standard stuff. I just have to align the chip and solder one corner first. Then I go to the opposite corner, align again, and solder it. And already it looks quite okay, but I will do some minor adjustments and solder the other corners also. Yeah, here a pin is still bent. I will straighten it first. I use my trusty knife. Good. Yeah, this looks nearly perfect already. Here another pin is bent. Let's make it straight. And let's secure this corner also. Good. One more corner. So at this point I'm ready to start with flooding with new solder. Yeah, after putting a little bit of flux there. And after cleaning the excess solder with a wick. Here I'm already done, and then I check all the pins to see if they're solid. Again with my nice knife. Now the three sides where the pins were straight, were done all just fine, but the side with the bent pins I had a lot of problems because some of them were bent in. Basically they lifted this side higher than the PCB, so in the end the whole row was not soldered correctly. So my advice is, okay, if you have pins that are bent left or right, it is easy. It's not a big issue because you can straighten them easily with a knife. But if you have pins that are bent downwards, it's better to bend them higher than the rest of the pins before trying to solder down the chip. And then after soldering the chip, you can deal with them one by one. Yeah, I had a lot of problems here to solve. In the end, the whole process, okay, for sure it's hard, but not crazy hard as long as the chip has straight pins. So after I went around and checked that everything was stably soldered, the last part is checking for shorts. And the best way to do this is by using the multimeter like that. So basically I go one by one. So here I have beep, here I don't have, here I have beep, here I don't have. If I have, there is a short. This is how I check both the connectivity and potential shorts. Now if I find a short, I can clean it either with a knife or with a soldering iron. So here testing again. Yeah, I just found a short. And here the knife, clean. The nice thing with this knife is thin enough, so it doesn't disturb the pins. Yeah, and this went for a while until I checked everything. And for sure, I made 100% sure I had no shorts before I tested it. Here, one more. Yeah, clean. More short. Yeah, I could have used the soldering iron there to clean it. So you get the idea. Now I didn't have to do all that with the 486 SXLC, just because, okay, the pins there are further apart. And it is easy to tell if there is any shorts just by looking at it. I mean, here, even though it looks okay, actually looks are deceiving. So this is the final result after some cleaning. Yeah, quite good. But of course, one side, yeah, a lot of bent pins. Now, of course, before I powered it up, I rechecked here to see that I don't have shorts on the data pins. And it was okay, but then when I put the BIOS chip, I had shorts. Yeah, I mean, the BIOS chip were also burned in the end. So here is the old chip. And if you go to diode mode, you put the positive on the ground and you check. Yeah, data 1 is basically still sorted. The others are fine, sorted. Also, there are more data pins actually sorted. And for sure I put it on the programmer and it was impossible to read. So the question now is, did this fail and burn the chipset, or the chipset failed and burned this? Hard to tell, but this has more data lines broken. So either way, I grabbed a new chip. Okay, there are many models that are very similar and basically any BIOS will work. But I got this PowerTech MB457 and I just got the latest one. I'm not really sure if this is okay for my motherboard, but yeah, I mean, might be different revisions, but it looks okay. Now this BIOS, I checked it, it doesn't have any hidden options, so yeah, I used it as it is here. So now, did this work? Let's see. Yeah, it works. However, okay, it didn't work the first time actually, and then I had to go back and recheck all the pins, and I found one here that was still unconnected. Yeah, the side with the bent pins. Now, as you can see here, I have already done some other modes too. I have done a battery mode, and I added here a PGA socket. With the battery mode, also I cleaned a bit around here. In the end, there were 1 or 2 broken connections. So let's see. Yeah, I removed the external battery connector, and I connected this too, and the positive battery terminal. Then, of course, I put a brand new pin header. Then, okay, for the battery mode, just place the socket here with a bit of extension on this side. The socket sits nicely there. I mean, there's only a bit of excess here, but it's not a problem. Then here, this resistor and this diode are the charging ones. I just removed both of them. And then this here is the reverse protection diode for the battery. And I just replaced it with a Schottky diode. So yeah, again, battery socket. These 2 components are removed. And this one diode is replaced with a Schottky. Then let's talk a bit more about the hardware that I'm gonna use today. First of all, a little bit more about this motherboard. Yeah, here we have both SIM30s and SIM72s. I just use a 72 SIM of fast page mode memory. I tried Edo memory. Well, okay, it works, but it behaves like fast page mode either way, so it doesn't really support Edo. Then the clock generator up here has 3 jumpers. Not all settings are documented, and I couldn't find the datasheet of the clock generator. But either way, using my ISA clock, it was quite easy to figure it out. Basically, the system posts with a default, 6 divider. So yeah, quite simple actually. I will put here a small table with all the values. Yeah, these are very standard ones from 20 MHz to 80. And of course I tried everything, and yeah, this CPU is marked for 33 MHz but actually works totally fine at 50. No extra voltage, no cooling, nothing. It can do really 50. 60 looks impossible, but okay, really I didn't try to push it too much this time. Now I actually have more of these chips in PGA form. This is the U5S and the U5SX. And yeah, all these perform exactly the same, so there's no point measuring all this. The chip I have here on the board is a U5SX, so same as this one. And the only difference is that this, the U5S, cannot clock that high, but this, the U5SX in PGA, yeah, did also 50, no problem. This one stopped around 40. Now regarding other CPUs, of course, mainly I will compare with these ones, the 486SX. Now the problem is these are 33 MHz chips, and it was very hard to run this at 50 MHz, but okay, one of these did 50 MHz with 5.2 volts and a Peltier cooler. Now regarding VGAs, this time I'm gonna use this one. This is Cirrus Logic GD5429. And yeah, this is a top performer similar to the Tencent and the TVGA, and just a bit below the Western Digital that I used last time. However, the difference is that this can handle higher ISA bus clocks. And yeah, here we will play with this. So now let's put this up and have a look. And first of all, in the BIOS. And these are my optimal settings. BIOS features. Okay, I have the external cache disabled because either way there's no cache. Nothing too significant here. And then chipset feature setup. Yeah, we have a lot of options here, but most of them are irrelevant. However, the ones that matter a lot. So auto configuration disabled, 0 weight states on memory, and fast page mode. These two are critical. Then these two are for the level 2 cache that either way we don't have any. This is for the strategy of the L1 cache. This also does not do anything because the CPU either way supports only write through. System BIOS cacheable and video BIOS cacheable. Very small to no effect also. Keyboard controller clock, okay, you can put it higher if you want, but yeah, I don't want to deal with this, so I just put it 7.2 MHz. So ISA bus clock, I have here 1/3. That means that the ISA bus is at 16.6 MHz. At 1/4 you get 12.5. And here 1/3 they worked, but I don't know, they give lower results. And yeah, only the Cirrus Logic improved. IO recovery 0, 0. This also gives a bit of performance. This is irrelevant. This local ready no delay. This in T2 and this no delay make a big difference. Flash cache when deturbo, force miss when deturbo. This I didn't check but might be useful. Basically means that when you are not in turbo, you disable the cache. This hold CPU %, and I thought that this is an option to slow down the CPU, but doesn't do anything. So this is regarding the tag, probably for the external cache. But again, because we don't have external cache, this does nothing. Probably this option means that more RAM is cacheable, and this might be better performance, I don't know. ISA bus refresh mode, fast is better. These two are signals that are normally generated by the keyboard, but if it is from the chipset, it's faster. And either way, here we don't have a keyboard controller, so yeah, chipset. This is irrelevant again. And then DRAM refresh method, there is RAS or cache before RAS. I checked, there is no difference, but okay, maybe this depends on the memories you have. If you have any problem, you might want to try the other option. So that's more or less the optimals here. I mean, this applies to more or less all motherboards with this chipset. It is just that here a lot of the options are irrelevant. The performance difference by doing all that is huge. In general, I think that you should never skip optimizing your BIOS settings. So now one more optimization. You see these Cirrus Logic cards, you can set the speed of the memory chips. There's a tool for that, the clmclk. I will put the link on the description. So right now the memory clock is at 50 MHz, clmclk 80, and this is the maximum 80 MHz. Well, this is huge change, but yeah, it doesn't make a difference in the benchmarks. Only some synthetic benchmarks on the VGA memory show some difference, but in real performance, not so much. You see, the real bottleneck is not the VGA memory speed, but there is a bus. Either way, okay, a little bit more, no problem. I will take it. So now time for the benches, and first of all, check it. Main system 11398. And yeah, already I know this is a totally ridiculous number, and this shows the strength of the CPU. Floating point 99.47, also very high. Yeah, we don't have a floating point unit, so this again the integer performance basically. Now video 6751 and 9126. Hard disk 4722 kilobytes per second, very high. Now with speed 85.1. With speed 8233. Yeah, these are very high numbers. And now landmark 307.2 and video again 8260. Cast check UMC, UMC, UMC. So here we have an unbelievable number on the cache speed 104.7 MHz, memory speed 46. Now system information 139.8. Let's see, check CPU. Yeah, UMC U5SX 50 MHz. CPU ID UMC, UMC, UMC. All as expected. Top bands 213, 214. Speed sys. And yeah, memory bandwidth 140.81. VESA memory 9158. CPU score 2739. And yeah, the numbers that really stand out here are the cache speed at 73.49 and the memory throughput 46.18. Hard disk speed also very fast, 4500 kilobytes per second. Now 3D bands 42.7, PC player benchmark 10.7, Doom low 77.2, Doom max 2385. Let's do a bit fast Doom. I think I will go with full V-spline, full everything basically, but then low details. And UMC 486 here. Let's see. This is not looking that bad. It's just low details, everything else is maxed out. 49.8. Very, very good. Let's see if I go here. High details, fast bus speed, I don't know. I forgot this. And reduce just here to get a classic high detail view. Yeah, this is as classic as it gets. 33.6. Again, not bad at all. So here we are with our nice comparison table. And yeah, I should have listened more to the Wikipedia page. Actually, the CPU is not just a bit faster, it is a lot faster. And for sure the comparison with the 486SX makes sense, because it is exactly the same conditions. But in the end, I had also to measure an SX2 at 66 MHz. And okay, ideally an SX2 at 80 MHz, but of course none of my SX2s were able to run at 80 MHz. So I have here the DX2. This is only a difference in some floating point tests, but more or less it performs the same. Now, of course, things are not that simple, because, okay, the UMC and the 486SX at 50 MHz have the same bus and same ISA speed, so exactly the same conditions. But with SX2 and DX2, this is not possible. So on the SX2 machine, the bus is 33 MHz, but then I changed the ISA divider to divide by 2. So the ISA bus is exactly the same, 16.6 MHz. On the DX2 80 MHz, I use the same divider for the ISA clock, so divide by 3. So this setup and this setup have the same settings, but this means that the ISA bus here is clocked lower at 13.3. I hope this is clear what I have here. So the UMC now, first of all, compared to the SX50, okay, there are some ridiculous speed-ups with everything regarding integer or cache performance. Yeah, something like 60% here, 30, 100%, another 30, then a 40. Yeah, very high numbers. Now, of course, because the VGA speed is more or less the same, in 3D game benchmarks, the benefit is not that great, but it's still very high. We have here 3D bench 23% faster, PC player benchmark 24.4, Doom low 10.6, and Doom high 11.2. So my total estimated is that the UMC is actually 27% faster, and the memory system is 41% faster. Now the SX66 is closer, especially it closes here the gap in the integer performance. But of course, because of the lower bus speed, we lose a bit in VGA speed. So yeah, here some are better, some are worse. And then 3D bench, we have 14.8, PC player benchmark 11.5, Doom low 10.8, and Doom high 8.6. Yeah, the UMC still wins. In general, it is something like 10.6% faster. Now, with the DX80, okay, we have to ignore all the floating point tests because it is unfair. And we see that the integer performance basically matches exactly. Then there is a mixed situation. And finally, we have here 3D bench 3.4%, PC player benchmark minus 10.1%, Doom low minus 2.9%, but then Doom high 0.5%. In general, okay, the UMC at 50 MHz is slower than the DX80, but the difference is actually quite small. I think the conclusion here is that this UMC U5S performs something like 50% faster compared to an SX2 CPU. So this at 50, it is something like an SX2 at 75 MHz. If it goes at 40, it's something like an SX2 at 60 MHz. So basically, in the end, the claim in the Wikipedia article is correct. So now here we are back with our motherboard. And yeah, what can I say? We did again a lot today. First of all, debugging, and I shared some tips on how to figure out the burned chipset, and then repaired this by replacing it. Then a few other mods here, okay, with the battery and the socket. Then a full optimization guide in the BIOS. And finally, a full set of benches and comparisons for this UMC green CPU. Now, the thing I didn't do was clock modding this motherboard, and in general going for the limits of this CPU. Though, of course, I did a bit of overclock at 50 MHz. Yeah, maybe not a bit because this is the 33 MHz version. But either way, the reason I didn't try to push it to the limits is because, okay, this motherboard actually has no cache. So even if I push it in the end, yeah, I cannot break any records here. Now the thing is, of course, this chipset is used in many full factor 486 motherboards, and for sure it supports cache and VLB slots, but unfortunately here nothing like that. Still, I somehow like this little motherboard. It's a nice little one, right? What do you think? So that's all for today. Don't forget maybe to like or comment, and yeah, see you again next time.